Honors Chemistry. We are starting a new unit, Unit 5, called Intermolecular Forces, and that's also the name of this next lesson, Lesson 20, Intermolecular Forces. So let's just talk about what that means. We've talked about mainly chemistry deals with chemical reactions. For example, if you take two hydrogen molecules and one oxygen molecule and you combine them in a chemical reaction to create two water molecules, you've created a new substance. You've taken two substances, hydrogen and oxygen, and created a new substance, water, by rearranging their molecules. When you take molecules, which are the products of covalent bonds, the question is whether those molecules are going to stick together or not. And just the simplest example is water. In its solid form, at very low temperatures, water forms ice. That's a solid. The molecules stick together tightly. They still have energy, they still wiggle, but they can't move around. And that's called a solid. If they have a little bit more energy, they can move around each other. They still touch each other, but they can move around each other. And that's what we would call liquid water. And then finally, if they're given even more higher temperature, more kinetic energy, the water molecules can break apart and form vapor or steam. So the intermolecular forces are what hold them together. And that's a function of whatever the substance is. Water molecules have certain intermolecular forces with each other that's constant. It never changes. What changes is how much energy you put into them, and that will determine whether they're going to be solid, liquid, or gas. In other words, how high the temperature is. If the temperature is very low, then those intermolecular forces between water molecules will predominate. They'll dominate the situation, and the water molecules will stick together. If you turn the temperature up, then the intermolecular forces don't change, but the kinetic energy, the temperature, starts to overwhelm them a bit, and they start to move around each other, but they still stick together. If you turn the temperature up even more, then they break apart. In all three of those scenarios, the intermolecular forces between the water molecules did not change. It was the temperature, it was the external factor of temperature that changed and that determined whether they were solid, liquid, or gas. So what we're going to talk about is intermolecular forces of different types of molecules in this unit. So there's three types of chemical bonds. Let's just review those. This is a review of what are the three basic types. There's only three ways that atoms bond together. One of them is metallic bonds, and we don't talk a lot about that in this class, but if you see over on the left, you see copper atoms, and they have electrons that are kind of floating around there, and that's called the electron C model. And that constant shifting of those negative charges to different locations between the atoms, they can move kind of freely. That's called the electron C model, and that's how metals stick together. That's how copper atoms stick together. It's how iron atoms stick together. It's how metal atoms stick together with other metal atoms. So that's called a metallic bond. Next is ionic bond in the center, and that's when a metal passes an electron over to a nonmetal. The nonmetals are the strong guys. They like to pull in electrons. The metals are the weaker guys. They give up the electrons. And so you have, in this case, a chlorine that has an extra negative charge. You have a sodium, Na, that lost a negative charge, so it now has a positive charge. So the positive and negative charges attract each other to form an ionic bond. And ionic bonds form what are called crystal lattice structures. So if you look at that cube, that's basically a grain of salt. If you look at salt that comes out of your salt shaker at home, it's cubic, and that's because it has this type of structure. Now there's one sodium, Na, for every chlorine, but it's not as though one sodium and one chlorine belong to each other like a molecule. They form this brick wall type structure. I either liken it to bricks in a wall or apartments in an apartment building. You can tell one from the other, but no one Na and one Cl belong to each other. They're bonded to all. The Nas are bonded to all the chlorines that are around it, and each chlorine is bonded to all the sodiums, Nas, that are around it. And so it forms that what's called a crystal lattice structure. Finally, over on the right, we have covalent bonds. And that's where you have two nonmetals, two strong guys. Neither one is strong enough to take the electrons away from the other. And so they share electrons and they form a covalent bond. Co meaning together, valent meaning valence electrons. So they share the electrons. Now, one of those two can be stronger than the other. Not strong enough to take its electrons away, but strong enough to pull them towards it. In this case, oxygen has a higher electronegativity than hydrogen. So while it doesn't totally take away the electrons from hydrogen, it does pull them in the direction of the oxygen. And that means that the oxygen side of a water molecule tends to be more negative because the electrons are over on that side. The hydrogen end is more positive because the protons that make up the nucleus of the hydrogen are kind of sticking out there, exposed like that. And so where you see those H's would be a plus sign for the proton that's the nucleus of a hydrogen atom. And so that side of the water molecule is more positive. So of these three, what we're going to deal with in this lesson is the covalent bonds because they form molecules. And so what we're talking about is not new chemical substances, not those hydrogens breaking off and the oxygen breaking off and forming some new substance. It's simply how much do they want to stick together? How much do molecules want to stick together? Inter means between, molecular means molecules. So it's the forces between molecules. So only covalent bonds form separate structures called molecules. Intermolecular forces determine whether molecules stick together or not. And this is a key point, that intermolecular forces, which we abbreviate IMF, are much weaker than covalent ionic or metallic bonds. So again, covalent ionic metallic bonds form chemical bonds, and they are much stronger. Intermolecular forces, which are not as strong as chemical bonds, simply determine whether the molecules are going to be a solid, like ice, a liquid, like liquid water, or a gas, like water vapor or steam. So, solids. They retain a shape, so those cubic ice cubes, as long as they're ice, are going to stay in that cubic shape. They're incompressible. You can't squeeze them down. We're not talking about crushing the ice cubes. We're just talking about you can't squeeze them and make them smaller. And they do not flow. So they're just almost like blocks of metal. Liquid, it takes the shape of the container. So that water that you see could either be in that glass, or it could be in a short, wide glass, or it could be in a really tall, narrow glass, but it's going to be the same volume of water. You're not going to increase the amount of water that you have. It is also incompressible. Even though water can slosh around, whereas solids can't, it's still, you can't push down and squeeze water. I'm not talking about stick your finger in it. I mean actually push it down and make its volume less. You cannot do that with water. It's incompressible. And it diffuses slowly. So if you drop a drop of food coloring in that water, it'll very slowly spread out throughout the water. Finally, we have gases. So they take the size and shape of the container. So you could have a bottle of perfume in a very small bottle, and on a warm day you open it up, and in 15 minutes you can smell that perfume in every part of the room. So the perfume molecules have spread out from being in a really tiny container that takes on the shape of that container to spreading out throughout the entire room. So they've increased their volume, they've increased the shape, or changed the shape so that it's the shape of the room. They flow and they diffuse in gas rapidly. In other words, the perfume molecules spread out in the air fairly rapidly. So intermolecular forces versus kinetic energy. So this whole subject of intermolecular forces, IMF, are a battle between kinetic energy and Coulombic attractions. Kinetic energy is external. It's whatever the temperature happens to be, and it's caused by higher temperature assisted by low pressure that allows molecules to separate. So the more kinetic energy you put into a substance, the more the molecules, or more energy the molecules will have, and the more they'll want to separate from each other. Coulombic attractions are the intermolecular forces, and they are the electrostatic forces of protons and electrons that attract molecules to each other. So Coulombic attractions are a function of what the substance is. Water molecules have a certain Coulombic attraction to each other. That's a function of the water molecules. The kinetic energy is a function of the environment. It's how much energy from the outside, what the temperature of the room is, that's going to act on those molecules. Generally, matter moves from gas to liquid to solid in two ways. One is you can reduce the temperature. So if you freeze those water molecules, let's say they're at 20 degrees, it's roughly room temperature. If you make them colder and cooler, they lose energy, and so they end up coming together and sticking together. Again, they have that Coulombic attraction to each other. At 20 degrees, that's enough energy to break them apart and cause them to be gas and to float in the air. Whereas at 0 degrees, they're going to come together and stick together because you have very little kinetic energy in them, but the Coulombic attractions therefore are allowed to take over and cause them to come together. The other is increasing the pressure while keeping the temperature constant and squeezing the molecules together. So this is just brute force. You can you can push down that piston there and squeeze them together and cause them to become a liquid or a solid just by increasing the pressure on the molecules. If kinetic energy overwhelms Coulombic attractions, then the molecules separate and exist as gas vapor. So that's what you're seeing here. There's enough kinetic energy, that is to say high enough temperature, that the water is boiling, or at least it might not be boiling, but it might just evaporate out of a glass. If you leave a glass out in a room for 2 days, you'll see the water level will go down. Some of that will become water vapor. If the kinetic energy and the Coulombic attractions are about equal, then the molecules stick together, but they can move around each other. So that's the way the water molecules would appear in a liquid. They can move around each other, but they're still sticking together. They're not separating from each other. If the kinetic energy is low compared to the intermolecular forces, then the molecules will stick together in fixed places. This produces a solid. So even in solids, the molecules are going to be moving around. Nothing in the universe stands still. There's nothing in the universe that's not moving. So even the molecules and atoms in a solid are moving. They're wiggling. That's called translational motion. They can't go from point A to point B, but they can wiggle back and forth where they are. So this is hydrogen sulfide. It's H2S, and it has a freezing temperature of negative 82 degrees centigrade. So as long as the temperature is below negative 82, they will be in this form. If you raise it above negative 82 degrees centigrade, they'll become a liquid. And then above their boiling temperature, they'll become a vapor. They'll become a gas. So even molecules in a solid move. Okay, now there's 4 types of intermolecular forces that we're going to talk about. And each one has a different strength to it, a different amount of Coulombic attraction between the two particles that it's acting on. So the first we're going to talk about are ion dipole forces. So table salt, which is NaCl, that's what that cube is there. Table salt consists of NaCl ions arranged in a lattice structure like bricks in a wall. So we've talked about that a number of times. Water is a polar molecule with the negative dipole pointing toward the oxygen atom. So let's remember what that word dipole means. Di means two, pole means pole. So it means it has a positive side and a negative side. So a water molecule is electrically neutral. It has the same number of protons as electrons in the entire molecule. It's just that the electrons are pulled over towards the oxygen. In this diagram, in this picture, that would be the red circles there. Those are the oxygen. So the electrons are going to be pulled over toward that side. That makes that side of the water molecule more negative. And the other side where the hydrogens are, the 2 white circles with pluses, that side of the water molecule will tend to be more positive. Overall, it is neutral, but it does have a negative side and a positive side. So the negative oxygen side of several water molecules point toward the Na, the sodium ion. So the sodium is a positive cation, and what they do is they go over there, and if you look at those sodium ions there, the blue ones, you'll notice that the red side of the water molecules is pointing towards them. So there's one down on the bottom, there's one down on the bottom right, and you'll see that the red side of the water molecule. So what happened is those water molecules went over to that cube, they ganged up on one of those sodiums, and they pulled it away from that cube. So that's why salt dissolves in water. So the oxygen side, the negative side of the water molecule stuck, of several water molecules, it's usually anywhere from 3 to 7, stuck to one of the sodium ions because that's a positive charge, so positive attracts negative, and it pulled it away from the cube. Similarly, you'll notice that with the green circles, those are the chloride anions, the negative chloride ions, you'll notice that the positive side of the water molecules, the hydrogen side, are pointing towards it. So they did the same thing. The positive side of other water molecules came over, was attracted to the negative chloride ion, and pulled it away from the cube. So by that process, salt dissolves in water. Okay, so there you see where it's pointing. You're seeing that the red circles, the oxygen side of the water molecules, are pointing toward the positive sodium ion. The positive hydrogen side of several water molecules point toward the chloride ion. So these are called ion dipole forces. The water molecule is a polar molecule, and that's said to be a dipole, two poles, a positive side and a negative side, whereas the ions are actually full positive negative charges. So the sodium and the chlorides are ions, the water molecule is the dipole. Ions have more of a charge than the dipole of the water molecule. Why? Because each chloride is a full 1 minus negative charge, and each sodium is a full 1 plus positive charge. Whereas the water molecule just has one side that's kind of positive and the other side that's kind of negative. That's why you need more than one water molecule to pull a chloride or a sodium ion away from the cube. Okay, so that's an ion dipole force. So both of these effects, whether it's the positive end of the water molecule or the negative end, both of those are called ion dipole forces. Now we're going to talk about dipole-dipole forces. Dipole-dipole forces attract polar covalent molecules to each other. So hydrochloric acid, HCl, is polar because a highly polar chloride ion pulls the hydrogen electron towards it. So those funny little symbols is delta, and the delta means that it's not a full negative charge, but it's a polar molecule that has a negative side, just like the water molecule did, and a positive side. So again, chlorine or chloride ion is much stronger, much more electronegative than hydrogen. So it doesn't take the electron totally away from hydrogen. It's not strong enough to do that, but it does pull hydrogen's electron over towards it. So the hydrogen electron gets pulled towards the chloride. That makes the chloride side of that molecule more negative and the hydrogen side more positive because it just has that proton in its nucleus kind of sticking out there without the electron being nearby. So if you have two HCl molecules, what happens is the hydrogen in a molecule is still attracted to its chloride ion. It's not going to leave its chloride ion. However, it also feels a weak attraction towards the chloride ion in a different molecule, and that's the dashed line you see there. So that hydrogen that's in the middle there is most strongly attracted to its own chloride in its own molecule, but it does feel a weak attraction towards the chloride in the molecule on the right. And that's called a dipole-dipole force. You have two polar molecules, two poles, and you have two of them there. So there's going to be a weak interaction between the hydrogen and the chloride where the dashed line is. But it is an attraction, and that's simply a dipole-dipole force. So below, the positive hydrogen side of an HCl molecule is attracted to the negative chloride side of another HCl molecule. The third type of intermolecular force are called London dispersion forces, named after the scientist who discovered them, not the city in England. So London dispersion forces are temporary changes in the polarity of a molecule due to the random movement of electrons. So dispersion forces are how nonpolar molecules attract each other. So if a molecule doesn't have a natural polarity the way a water molecule does with a positive side and a negative side, then they can still be attracted to each other by London dispersion forces. So let's see how that works. So here you have electrons of hydrogen atoms just kind of, and it could be other types of atoms just going around and around. Now let's say for some reason that we can't explain, the electron of atom number 1 settles on the right side of its nucleus. So it's over there on the right side of atom number 1. What that's going to do is push the electron in atom number 2 away from it, because electrons repel each other. Negative, negative repels. So that's going to push the electron in atom number 2 also over to the right side of its atom. What that's going to then do is push the electron in atom number 3 over to the right side of its atom, of its nucleus. So you'll notice that the electrons are all lining up to the right side. That means if you have a lot of these bonded together, these hydrogens bonded together, they're going to have the right side of them is going to be more negative, because that's the electrons are being pushed over to that side. The left side is going to be more positive because the protons are left over on the left side. The other thing that's, and there you go, there you see that. The other thing that's going to happen is the electron in atom number 1 is going to feel a weak attraction to the proton in atom number 2, similar to a dipole-dipole, but it's even much weaker. And then also the electron in atom number 2, it's going to push away the electron in atom number 3, but it's also going to feel a weak attraction towards the proton in atom number 3. So this is how nonpolar molecules take on a temporary polarity. It's not a permanent polarity the way a water molecule is, where the electrons are always over on the oxygen side, but it's a temporary polarity. If you have enough atoms doing this, however, it can form a fairly strong bond, and we'll show that in just a second. So when the electron in the hydrogen atom on the left moves to the right side, it pushes the second atom's electron to the right. If this effect repeats throughout many atoms, it creates a temporary polarity that attracts the atoms to each other, and also makes one side of that molecule negative and the other side positive. So dispersion forces, LDF is London dispersion forces, sometimes we just call them dispersion forces, are small but can produce a stronger attraction between large molecules with many electrons. So here we have a gas. It's about the smallest type of nonpolar molecule you can have. It's methane gas, CH4. It is nonpolar. It has weak London dispersion forces because it has only 10 electrons. So count them. Carbon has 6. Each hydrogen has 1. That's a total of 10 electrons in that molecule. Methane has very weak LDF, London dispersion forces, and is not attracted to other methane molecules. So there's just not enough electrons to make a strong enough dispersion force. Now, if we get a bigger molecule, it will form a liquid. So this is octane. It's C8H18. It has 66 electrons if you count up all the electrons in 8 carbons and in 18 hydrogens. This is strong enough to make octane a liquid with other octane molecules. So octane is a form of gasoline that people put in their car at the gas station, and as you know, that's in liquid form. So they have a stronger attraction to each other, and they're able to form a liquid. Finally, our last example is an example of a solid, and this is paraffin. And you can see it has C40H82. That's a pretty big molecule, and it has 322 electrons. This many electrons form strong enough attractions to make paraffin a solid at room temperature. So paraffin being candle wax. As you know, it'll melt when you light the candle, but at regular room temperature, it's a solid. And there's some that are even stronger. The asphalt that they put in the streets, that black kind of tar stuff that they put in the streets, is also a hydrocarbon, and it has very large molecules, and therefore it forms a very solid substance that they can actually pave the streets with and that cars can drive on top of. So the shape affects the strength of London dispersion forces. Longer, flatter hydrocarbons, such as N-pentane on the left, form stronger London dispersion forces than round neopentane molecules, the ones on the right. because the ones on the left fit together tighter with less space between them. So since they're basically lying on top of each other, those weak forces can have more of an effect on them and hold them together tighter. And so the shape has an effect on the strength of London dispersion forces. The ones on the right kind of look like jacks that maybe some of the girls played with when you were little. They don't lay neatly on top of each other, so the London dispersion forces are weaker with those kind of rounded molecules. Okay, now we're getting into the fourth and the strongest of the bonds, and that's hydrogen bonds. It's a little more complicated, so kind of follow this. So hydrogen bonds occur when a hydrogen atom, so it has to be a hydrogen atom, is bonded to one of the three most electronegative second row elements. That would be nitrogen, oxygen, and fluorine. Those are in the upper right-hand side of the periodic table, so they have high electronegativities. So when oxygen pulls the electrons of hydrogen toward it, an exposed hydrogen nucleus, a proton, is left exposed. So let's just take the water molecule on the top. The oxygen is highly electronegative, so it pulls all the electrons towards it. That means the hydrogen atom, which was originally a proton and an electron, gets its electron kind of pulled away from it. Not like an ionic bond, but it does get pulled away. That leaves the proton part of the hydrogen just kind of sticking out there exposed. So you have these two positive charges on each water molecule sticking out. So this proton, the proton is attracted to the lone pair of another molecule with a nitrogen, oxygen, or fluorine atom. In this case, it's other water molecules, so it's other oxygen atoms. The hydrogen atom has a fairly strong attraction to the other atom, though it is not nearly as strong as to its own covalent bond. So if we take this proton right there from that hydrogen, it's going to feel an attraction to this lone pair of electrons down there on that water molecule. It's not nearly as strong as the attraction it feels to its own molecule, but nonetheless, it's enough to attract this entire molecule down there. So it doesn't jump over to these lone pair. It just, the entire molecule moves down there, and they kind of attach right there. All right, and then this one can attach to a different water molecule. So now we're going to look at a mix and match of the nitrogen, oxygen, and fluorine. So for a hydrogen bond to occur, a hydrogen atom must be attached to a nitrogen, oxygen, or fluorine, and it must be attracted to the lone pair of another nitrogen, oxygen, and fluorine. So the two things, it has to be a hydrogen atom that does this, and it has to be attached to a nitrogen, oxygen, and fluorine. Oftentimes in hydrocarbons, you'll see hydrogens attached to carbon atoms. Those cannot form hydrogen bonds. Why? Because the carbon is not electronegative enough to pull the hydrogen's electron towards it enough so that the proton of the hydrogen is really exposed. It's really sticking out. So that's a lot of times a test question on various standardized tests. They'd like to show you a carbon-hydrogen bond and ask you if that can form a hydrogen bond with another molecule, and the answer is no, not if it's carbon. It has to be nitrogen, oxygen, or fluorine. So let's look at the first pair, the two water molecules over there on the left. So you see those are both water. They're oxygens and they have two hydrogens, so that's H2O. And they're attracted the way that we showed before on the previous slide. That one plus, where the dash line is pointing towards, is going to be attracted to the lone pair of the other water molecule down on the lower left. Now, here in the center, a hydrogen atom on a water molecule, hydrogen bonds with the lone pair of a nitrogen. So if you look at that dash line that's in the middle between a hydrogen proton, that's the plus sign, and the lone pair, it's on an ammonia molecule, so it's being attracted to the lone pair of the nitrogen there. So you can mix and match. Okay, and there you see the hydrogen bond between a proton, a hydrogen atom that's attached to an oxygen, and the lone pair on a nitrogen. So you can mix and match these hydrogen bonds. So hydrogen bonding works because nitrogen, oxygen, and fluorine pull the electrons away from the hydrogen so completely that an exposed proton is left sticking out from the other molecule, and that's attracted to the lone pair of either an oxygen, nitrogen, or fluorine. So the hydrogen bonds of water, H2O, are stronger than the hydrogen bonds of ammonia or hydrofluoric acid. Why is that? There's one hydrogen on a water molecule for each lone pair on another water molecule, on other water molecules. So that's a perfect match. So for every hydrogen you have that could be bonded, that could create a hydrogen bond on a water molecule, you have two lone pair to which it could attach. Now, this never happens, this situation, where one molecule, the two hydrogens on one molecule attach to two lone pair on another molecule. That would have to be two different molecules. So the hydrogen, one of the hydrogens would attach to the lone pair on one water molecule, and the other hydrogen would attach to the lone pair on a different water molecule. It's never like that. I'm simply showing that to show how it's a 2-to-2 correspondence. So it's a perfect match of protons to lone pair. Ammonia has only one lone pair. So if you look down there, look at those ammonia, they have one lone pair for every 3 hydrogens. So each of those has 3 hydrogen that want to find a lone pair, but each one only has one lone pair. So it's a mismatch. It's like a dance. If you have 3 times as many boys as girls, then a lot of the boys won't have a dance partner. Okay? And so that's the situation there. You have 3 times as many protons, those plus signs, as you have lone pair. So no lone pair to bond with in those 2 cases there. If we go over to the right, we have the hydrofluoric acid molecule. Hydrofluoric acid has only one hydrogen proton for every 3 lone pair. So that's the opposite situation. If you have a dance and you have 3 times as many girls as boys, then a lot of the girls won't have somebody to pair up with. So that's the situation there. So because there's a mismatch in numbers of lone pairs to hydrogen atoms in the ammonia and the hydrofluoric acid, they're not going to bond as strongly. They do form hydrogen bonds, but they don't form as many or form them as strongly as water, which has a perfect 2 protons to 2 lone pair ratio. So no hydrogen to bond with over there on the right. So water hydrogen bonds most efficiently and has the strongest hydrogen bonds. So comparing the intermolecular forces. Generally, the following is the order of strength of different intermolecular forces from weakest to strongest. So generally the weakest are the London dispersion forces, and they're the weakest because they consist only of temporary dipoles, and they're really effective only in nonpolar molecules. Now, all molecules have London dispersion forces. It's just that those that also have dipole-dipole, ion-dipole, or hydrogen bond forces, those predominate over the London dispersion forces. But all molecules do have them. The next weakest is dipole-dipole. They're next because they consist of the positive, negative ends of electrically neutral molecules. So in other words, they're not full 1 plus 1 minus charges on those molecules. It's just kind of a positive charge, kind of a negative charge on those molecules. So they're not quite that strong. Next is ion dipole are stronger because they contain a fully charged ion with the end of a molecule of the opposite charge. So that's the water molecule being attracted to either a sodium or a chloride ion. And finally, the strongest are hydrogen bond forces. They're the strongest. Hydrogen bonds formed by water molecules are stronger than other hydrogen bonds, as we saw in the previous slide. Okay, so that takes care of this introductory lesson to intermolecular forces. Again, intermolecular forces determine the attraction between molecules. And they each, for any substance, there's a particular coulombic force between the molecules, and whether the molecules form a solid, liquid, or gas depends on external factors such as temperature and pressure. Higher temperature will cause the molecules to come apart, lower temperature will cause the molecules to come together. So that's it, and we'll talk about some of the other characteristics of intermolecular forces in the next lesson.